Hello everyone, good morning. Today we will go into the third part of chapter 2, right? Regarding block diagram and reductions of multiple subsystems. Today's slides would be in a PDF form if you notice later on, right? Because of some updates not taken place on the PowerPoints, right? Okay, so I hope still works as usual, right? So last week we have discussed about how to model a mechanical system into a transfer functions, right? So today our goal is to complete the outcome of this course, okay, which is the block diagram simplifications. Okay, our intention is after we able to model a system into the corresponding transfer functions, now we are going to display them or connect them into multiple blocks diagram, and after that we try to simplify the whole process. Okay, so generally we have two approach in analysis and design of a control system. Okay, here we call feedback control system because most of the time we intend to have a kind of feedback, okay, minimum a kind of feedback like what is happening at the output, okay, and we use that to improve our input, okay, in order to reach the target output, okay, at the end, right? So there are two approach, okay, one is classical and another one is modern, right? So, and our focus in this course will be mainly on the frequency domain, right, which is about converting the differential equations into a transfer functions, okay, and we try to model and approach or analyze the system, okay, using these transfer functions, right? Therefore this is very important for us to be able to simplify the block diagrams, okay, into a simplified transfer functions. Okay, we have multiple block diagrams which contain multiple transfer functions. When we simplify all this block diagram into one or maybe just a set of familiar diagram, then we can further simplify the transfer functions into one simple transfer functions, right? Then on the time domains approach, as we usually see in the form of t, okay, so our time functions, okay, we have a y as a functions of time that would give us a flexibility to deal with various conditions such as nonlinear systems, okay, and so on, right? But for this course, okay, for this fundamental course, okay, our focus will be just to linearize our system, okay, and check whether the system is stable or not, right? That's why we would focus more on the frequency domains method, right? Okay, in order to represent a systems, okay, that consists of multiple subsystem, okay, we have two methods, okay. The first one would be the block diagram, as our title of this sessions, okay, which is usually suitable for frequency domain analysis and design, okay, whereas for the signal flow graph, okay, that would be more convenient for another type of analysis. We call that as a state space analysis, okay. Again, our focus is block diagram, okay. Signal flow graph, okay, we will just go through it, that's it, all right, and whenever times come that we really need it, then we will approach it accordingly. So the general procedure in drawing a block diagrams would be like the course outcome itself, okay, we should able to first write the equations, okay, of to describe dynamics behavior of our components, just like a spring, mass and damper system, right? Then we take Laplace transform and maybe we assume a zero initial conditions, okay, that is without the input, okay, so zero initial conditions. So we take the Laplace transform, and now we represent the Laplace transform equations into the block, okay, into a block form. All right, so after that we will assemble all these multiple blocks into a complete block diagrams, right? So this is a simple block diagrams as we shown, okay, so there is an input, okay, there is an input and there is an output, okay, and this input is going through a system, okay, and this system can be a subsystem, okay, as we say, it can be a very big system, okay, that consists of multiple blocks. All right, so this system itself is where we would usually write our transfer functions, right? And after this input going through this transfer functions, okay, it will get transferred, okay, and result to an output, right? So this is a simple block diagrams, okay, that consists of a block and the signal, right? So you can see that the signal flow or directions is being signified by the directions of the arrow, right? So usually we will write the transfer functions inside the block, right? And then the representations of signal, maybe we can say this is R, this is C, and so on, right? In next to the arrow, okay, or the line itself, right? So from this transfer function, as we have learned before, okay, transfer functions generally describe the relationship between the output and the input. So we have a ratio between them, okay, so output over the input. So this gives us the H, right? The transfer function inside the block, right? Output over input, okay? So C over R. Okay. Now, in order to represent the diagram, we have we have several representations of signal operations, okay? We can sum them up, okay, do an additions or subtractions of a signal itself, okay, through this summing junction or summing point, right? So we have this circle, okay, where the signal maybe come in, go out, okay, come in and come in, right? So whenever they come to these junctions, okay, usually we will represent with a circle, and you can see that there is a sign, okay, plus, minus, or minus, plus, minus, or and so on, right? So this tells us how we would want to do the operations, okay, at this point itself, okay. So when we see a plus, meaning to say this signal R will be added, okay, or at this point, right? So we will plus R, okay, at this C signal come over here, we will also adding in, okay. Then when this signal B come here, there is a minus, okay, so we will minus this signal, right? So eventually that would become our output. So if mathematically to represent this one, we would say that the E, okay, the output would be equals to the C plus R minus B, okay. So we can represent this diagram mathematically as E equals to R plus C plus B. So this summing junctions is important for us to do a comparisons of the component, okay. The comparisons meaning to say, remember previously we talked about the arrow signal, okay. The arrow meaning to say if we don't have this C, okay, this E represent an arrow which comparing the initial input, okay, we minus it with the output, okay, and see what is the error, the difference between the input and the output, right? So that would be the purpose of comparisons. At the same time, we want to add them in, okay, as well, okay, sometimes, right? Then there is also another type of signal operations where we branch off, okay, our signal, right? So from one single point, then it go into several branch, okay. And since this is a branch off, okay, so whatever comes in should be equals to what is going out at the branch. So if the signal is R, then for sure what you receive at every single branch that you going to tap into at this particular branch point, okay, should be same, okay. So R, you can see R everywhere same, right? So we remember at this point we don't do any operations, we don't do plus or minus. Okay, we just use this signal, we branch it into different road. Okay, that's all. All right. Now to simplify, okay, this is the main component of a block diagram. Okay, for a feedback control system. Okay, we would have an input. After we compare it, we have an error signal. Okay, this error signal will go into our system. Okay, and then we output it. So this output we will now branch off. Okay, branch off and tap it back to this summing junctions. Okay, to do a comparisons between them, so we can compare between this input and output. Okay, and so on. So this is a form of a feedback control system that we should able to spot. Okay, meaning to say when you see it, then immediately you know this is a feedback control system, right? So if you refer back to any books and so on, right? So you can usually we will see that the input we will have a plus sign, and the feedback that coming back we will have a minus, so that we use the input, we minus it with the output to get the difference between them. Okay, that will serve as our error. Okay, so usually we will have this plus and minus sign. All right, so if later on what we get we will discuss later. Okay, on the plus and minus sign. Right, and then when we have multiple block diagrams, now this is where you need to do kind of simplifications, right? So again, the previous one is one of the form that you can see as a familiar form. Okay, the feedback control form. Okay, that you will intend to group them in that form, right? If you can see, right? Then also if it's happened to us that there is a multiple block, okay, cascaded in a series, right? Just like in this diagram, so you have G1, G2, G3, right? And so on, right? So what happens is that this signal that comes in, okay, to G1, when it goes through G1, the output of it will be G1RS, right? We multiply with that this, okay, signal being transformed. Okay, we multiply by this, right? Then this signal going into this second block diagram, right? Then again it's being multiplied again with G2, okay, and being transformed in this that kind of signal, and further on it will keep cascading this kind of signal, okay, transform signal in by multiplying the transfer functions, right? So this is how we can represent it, okay, visualize it in the signal form, right? So since we know that this is the output of the signal, what happens is that if we compare, remember what the transfer functions means is that the output divided by the input, right? So if we take the output divided by this input, okay, we can remove this RS, right, this input signal. So eventually our transfer functions, okay, the simplified transfer functions will be our cascaded transfer functions, okay, of this series block diagram, okay, series of block diagram G1, G2, G3, right? So it's being cascaded in this way, right? So we can simplify this familiar cascaded system into a single block diagram as shown is below, right? So this is a way to simplify it, right? Then for sure also there is a parallel system, okay, where the signal goes to a point and then branch to different transfer functions, okay, to do different signal, okay, and then they come back, okay, to one point, okay, before it's being output, right? So you can see that at this branch point this signal is R, R and R, okay, but then going through different transfer functions our signal will differ, okay, so this will become G1R, okay, this one G2R, this one G3R, right? Then again when we combine these three signals together at some point, right, at some point, okay, So let's say this is a plus plus minus, let's say, right? So this could be plus minus minus and so on. It depends on the design of your system. Okay, so let's say this is plus plus minus, then you can see that this one would be G plus G2 minus G3. Okay, since this is minus, right? So this is where I've mentioned previously, plus the sign will determine this whether we should add or minus, right? So this plus minus, okay, and we can how to say group them, okay, and we have a common input over here. Okay, so using the same methods, okay, if we intend to simplify this whole block, right, this parallel system, okay, we just compare it with the output and the input. Okay, so the input signal will now remove and we can simplify it as a G1, G2, G minus G3. Okay, G1 plus G2 minus G3, right? So you can see that in series we multiply, okay, the transfer functions, whereas in parallel we add or subtract, okay, the transfer functions, okay, that we have, okay, in order to get the simplified transfer functions for multiple parallel subsystem. All right. Okay. So now come back to the feedback system. Okay, so generally we have this kind of feedback system, okay, as shown here. Okay, so this feedback system, okay, it can go through multiple blocks, right? So we can have a transducer over here, we have a controller over here, then we have our plant. This plant can be any machines, can be any process, and so on, right? And then the output of it, okay, whether this output can be in the form of temperature, flow, or whatever it is that we intend to measure and control, right? So remember, this is our intentions to control the parameter that we want to, right, by represent them into block diagrams, right? So this can be coming back, okay, as a signal, right? And this signal again will go through an output transducer. Remember, in the slides previously, okay, we have this transducer can be a analog to digital converters and so on, right? So that would be the output transducers, right? And then we go through a feedback transfer functions or a controller kind of machines to interpret, right? And then we feed it back, okay? So this is the whole process. It can be going through multiple devices, okay? So and each of the characteristics of the devices can be represented by the blocks, right? If we able to represent them into blocks, then that our accuracy of the transfer functions or the control would be more high, okay, higher accuracy at the end, right? So the more blocks that we can model, okay, then the accuracy of our control would be higher, right? But for sure we may not able to model every single component, right? We may not able to do that, right? So it depends on the influence, okay, being put into the effect or effect, okay, to our system itself, okay. But for sure today's when we come to a digital world, okay, when we start to design on the inside a computer, then all these characteristics can be now captured better, right? So if we have a especially electronics component, okay, so all these electric component can be visualized, okay, we just drag and drop, okay, into a circuit, okay. So if it is a circuit, then it would be much easier, okay. We just have to tell the characteristics of each of these resistor, inductance, and so on, okay? And then we can simulate a very complex system, okay? But then when it comes to a larger system, then we have to identify which block that really contribute to the whole output that we desired, okay? That would be our main block, right? So the rest we may or may not, okay? It depends on how much accuracy you want to control, right? But anyway, okay, so this is how we would see a feedback system, okay? And then from that, okay, we can see that there is this familiar blocks, okay? This is blocks being arranged in what we call series form, right? Same thing at the output directions, okay? They are being arranged in the series form. So immediately we can see that when they are series, then we can just multiply these transfer functions into G2, G3, right? So at this side we can have G1, H1, H2, right? Okay, and also later on we will deal with this G1, okay? How we can move this block diagram across the summing point, okay, or a break off or branch point, okay? So if we able to move this block over here, okay, then we can see that there are 3 blocks being cascaded, right? So we just do what the usual way, okay? We cascade them together into a single simplify them into a single block diagrams, okay? And at the feedback directions we also group them into one single block diagram. And finally you can see that this is the, as I mentioned previously, this is a familiar form of a feedback control system, okay? One input without any blocks, okay? Going in, there is, after the error, there is one what we call feed forward block diagram, okay? And then a feedback block diagram, right? So this is a familiar form that we want, okay? If we can able to group them like this or just a straight line, okay? Either straight line, open loop type, okay? Or in the form of a closed loop type, okay? Then this closed loop type, okay? This closed loop type, we can represent it with this transfer functions, okay? So immediately we can see that these transfer functions, remember as I mentioned previously, this is plus, and the feedback coming back should be minus most of the time, okay? So when plus and minus, okay, then our transfer function would be the feed forward transfer function divided by 1 plus feed forward multiplied by feedback transfer function, okay, fg, okay? So if this is minus, then this would be plus, right? Then if this is plus, then it should be minus, okay? So they have these relationships, okay, right? So remember, once we can group them into this form of feedback block diagram, then immediately we can simplify them into these transfer functions, right? So this is the idea of combining them or simplify them into a familiar form, okay, of a system, right? So how we actually arrive or derive these equations, okay, or these transfer functions, right? So this is our considerations, okay, a simple feedback control system diagram, okay? So this is error, this is feedback, this is our output, and this is our input, okay? So here what we can see is that the ratio between the output and the error signal, okay, will give us the transfer functions of G, right? We can see that, okay, we just remove, okay, assuming the rest is not there, okay? So after going through the transfer functions of G, then we get Y, right? So immediately we can see that the ratio of output divided by error gives us the transfer function of G. Okay, similar to the feedback. Okay, since this is branch off. Okay, so this Y will now go here. Okay, so the Y signal after going through the H transfer functions, we would get B, right? So in other words, the relationship between the feedback and the output signal will give us the transfer functions of H, right? So now after that, we can also see another form. Okay, we call this as like a circle. All right, so assuming this error signal, okay, we just blur our eye, okay, on the input and output. Okay, so this error signal will actually go through G and then go through H before it comes to this point, right? So this is the flow of signal, okay, of error, okay, that is being fed back to, okay, to the summing point, right? So if we just take into the account of comparing the ratio between this B and the error, the E, okay, then that would be, this is in a series form, right? So we just multiply them, right? So G multiplied by H, okay, so we get this B over E equals to G over H. Okay, so we can see that this so-called open loop transfer function, a loop gain, okay, due to this, right? So eventually, if this H, okay, this H, if we don't go through any transformations or gain or block diagram, okay, we just tap this signal and feedback, okay, we call that as unity, okay. When the transfer functions for the feedback side, this H is unity, okay, so we will put H as equals to 1, right? So eventually this B signal will be equals to H, okay, this B signal will be equals to Y, the output, okay. Then in that sense, this just like the feed forward is the same like the closed loop, okay. So eventually it looks like it's the same, right? So now further forward, okay, is that we can derive the error signal, okay, this error signal, okay, going through this summing point, okay. So remember, we want our summing point itself, okay, where we can see that the error signal is actually the input minus the B, okay, the feedback signal, right? So we can see that this error is equals to R minus B, okay. So we have R minus B, okay. So here we see that from this form itself, okay, remember previously we have the relation between for the transfer function of G and H, okay. So if we want, okay, we can actually rearrange, okay. So to substitute this B, okay, out, so we can use this transfer function such that B equals to Y multiplied by H, okay, Y multiplied by H. So this we substitute in, then we get this YH, right? So next is that this E, the error itself, okay, can be rearranged as Y divided by G, okay, Y divided by G. So we substitute this over here, Y divided by G, okay. So once we have this, okay, Y divided by G, okay, our intention is to derive the signal such that it shows the feedback control system by comparing the output, the Y, divided by the input R, okay. So our intention is y divided by r. So based on these equations, now we can rearrange again. Okay, so if we rearrange this one, this g multiply over there, okay, this g multiply over there, right? Then the r, okay, put it back, or how should bring it out, okay, of the equations, okay, by also divide by r, okay, bring it over here, okay. Okay, so we would get the g divided by 1 plus g multiplied by h. Okay, so we would get this particular form. Okay, so we just rearrange this, okay, y, okay, group them together, okay, and so on, right? So mathematically you can get this form, right? So we can see that this happen, okay, when the feedback signal is being minus. Okay, so it's minus over here, then we get a plus over here. Okay, so if we change this to a plus, then we will get negative over here. Okay, that's it, the way or why we get this this simplified overall transfer functions to represent the feedback control systems. Okay, this feedback control system, right? So we will call this transfer functions as a closed loop transfer functions. Okay, so eventually closed loop transfer function is g divided by 1 plus gh. Okay, 1 plus gh, right? So if the feedback is a unity, then it will be g divided by 1 plus g, right? That's it. Okay, so always remember this, okay, that because we will keep using this from time to time onwards. Okay, so next, as we have seen previously, sometimes there are blocks that are actually located maybe before a summing point or a break off point and so on. Okay, so how we can actually deal with them? Okay, we would want to move the blocks, okay, in order to create a similar form. Okay, so that so-called familiar form, okay, can be in the form of, as we have seen previously, at the cascade, parallel, or in the feedback. Okay, so we try to arrange them in this kind of form. Okay, so if possible, we do the cascade and parallel first, okay, before we group them into the so-called feedback form itself. Okay, so sometimes we want to move this over here, okay, so that we can do some operation on this this side, right, the right hand side. Okay, sometimes we will want to move it in, okay, so that we can form maybe a closed loop for our transfer functions. Okay, so this is our intention, to move the blocks, okay, to create a similar form, right? So how we can move it, right? So moving a block, okay, so this block, move it out, right? So let's say this block, we move out of this summing junctions. Okay, so it can be in this way, right? So what happened is that we would now see, okay, how actually the signal have changed, right, before we create an equivalent to it. Okay, so this signal coming in, okay, going through these summing junctions, okay, when there is a minus x coming in, okay, so this error signal here would be r minus x, right? It's the r minus x. So when this r minus x going through these transfer functions, okay, that meaning to say this r minus x will be multiplied by the g, okay, the whole thing multiplied by g. Okay, so this is our final signal, okay, coming out, okay, at this point, right? So our intention now is we have to move this over here. Okay, we still maintain the input of r, okay, the output of g multiplied by r minus x. Okay, but then once we move it over here, okay, so once we move it before the summing junction, so what happens is that this signal coming in or coming through this transfer functions g, okay, then we will have gr, okay, before we go through this summing junctions, okay. So this would be gr minus x, okay, if we don't add this, right? So meaning to say, if we intend to move it out, okay, of these summing junctions, we have to also add another block, right? So that the effect of this block moving before the operations of additions or subtractions, okay, it should be there, okay, before that, right? So we have the gr, and then this x going through the g functions, okay, we have gx, okay. So when we sum them up together, then we have the multiplication of g multiplied by r minus x, okay. So this is the idea of it, right? So remember, when we move it out, okay, before the signal coming into the summing junctions, then we would add the block, okay, to every single signal that coming in, right? So the signal coming in, if we have the third one coming in, then we have to also add this block diagram to the additional signal coming in, right? So this is the idea, so that we don't disturb the final output of the signal, okay, after the summing junctions, right? So we could say that this is equivalent, alright. Then on another side is when we have a block, okay, before the summing junctions, okay, and we intend to move it in, okay, or after the summing junctions or operations of plus or minus, okay. So if we intend to move in, now the problem is that it will now affect both line, okay. Previously when we put it out, okay, the signal will be actually come from these two line, right? Okay, but now when these transfer functions only act on one single input signal, okay, so what happens is that when we move it in, okay, or after the summing junctions, it would now also affect the other line, okay, the another signal, okay, coming into the summing junctions, okay. So how we would see it to happen is that this r going through the g transfer functions, we get gr. Then going through these summing junctions, we will have gr minus x, okay, gr minus x as the output, okay. So our intention is to maintain such that after we move this block, okay, our output still gr minus, sorry, this should be x, okay. So we should still maintain as gr minus x, right? So this is our intentions, okay. So this should be x, okay. So what happened is that in order to maintain this one, okay, by moving this block over here, the g transfer functions over here, then we would have to add 1 over g, okay, to the other line, okay. So if this coming in, okay, if we have another line, so we have to add a block, okay, of 1 over g, okay, so that we reduce the actual signal, okay, or increase the actual signal, okay, depends on whether the g is small or big, all right. So we have to mitigate this effect, right? Because originally this should be 1, okay, x coming in, right? So we would want to reduce this signal, okay. So we can see that if this is g, this is x going through 1 over g, then we will have x over g. So this x over g, when we come into this summing junctions, okay, we would get, after the summing junctions, we will get r minus x over g. So once we multiply by the g transfer functions again, then we will cancel out this g, and we multiply the r with a g. So eventually we get this signal equivalent to the previous one, right? So remember, if we move it past the operations of the summing junctions, then the block will be moved, okay, but other lines will be affected by dividing with 1 over the transfer functions. Okay, so this is how you can move the block diagram or the blocks, okay, before an operations of summing junctions or after the operations of a summing junctions. Okay, then also we have these relationships of moving the transfer functions pass through branch. Okay, so what happens is that this R, after going through G, okay, is very straightforward. We will get GR, right? So this GR signal will be transferred to every single branch. Okay, so if we intend to put it on the branch, not on this main pipeline, right? So we just have to add it to every single branch. Okay, that's it, right? So that this is now into every single branch, right? So the output of the signal at every single branch would be equals to GR. Okay, then another form is that it could be in one of the branch, and now we want to move it to the main pipe. Okay, it can be at one of the branch, we move it out to a pipe. Okay, so now here you can see that I purposely put it in this way, okay, so that you in the later exercise or in the future, okay, you will sometimes see this form as well, right? So you have to be able to recognize that all this line is actually a signal. Okay, here we have one branch, okay, here we have another branch, okay, so they are branching off from one line, right? So eventually this point and this point, okay, it could be the same point, right? Okay, so you have to recognize that if there is no block diagram in between here, this point signal is actually exactly the same as this point, okay, and so on, right? So these 2 points can be combined together, okay, just like this, right? So this could be as the same as this, okay. So you have to be able to see this, okay. Don't later you will see that, or you have a block, okay, you have to transfer over here, then you transfer over here again, okay. You don't have to do this, okay. Just recognize this particular point, right? We don't see this as branch into 2, and then over here we branch over into 2 again, okay. Basically this is only directly branch into 3 branch, right? So now our highlight would be this, okay. We intend to branch or bring this transfer function inside the branch, okay, into the main pipe, okay. So into the main pipe. So if we move it here, now we would want to see what is the effect, right? So for sure this one will have the signal of GR, okay, because they have a transfer function over here. So immediately if we put it here, it would not disturb anything, right? So it will go through and then everything will be the same, right? But the only problem is once we put it into the main pipe or the parent pipe itself before the branch, okay, then it will also affect the other branch, okay. So what we need to do is we have to remove this effect, okay, or this signal at every single branch by dividing it with the G, okay. So we just add 1 over G to other branch, okay, that are not affected, okay. So this is the idea behind it, right, on how you can move them pass through a branch or pick off point. Okay, now we go to questions first, okay, before we go through the examples. Okay. Any questions so far? Okay, so as usual, as we while we wait for the questions, okay, if there is, okay, then we continue, okay, so that we can address that later on, right? So let's go through these examples of we have well, 3 summing junctions, okay, and then this branch into here, then it branch, right? And there is multiple blocks, okay, so we have G as the so-called feed forward transfer functions, okay, then H as the feedback transfer functions, okay. So you can notice that the sign would be minus, plus, minus, and so on, right? So as we see previously, okay, so this point signal is exactly the same at this branch and this branch and this branch. So basically all these 3 points can be same point, okay, with this, right? So remember with that, right? Then also when we combine this together, okay, this summing junctions, okay, this point one after the other, okay, basically we are doing operations by continuing minus, plus, and minus, okay, to our main signal over here, okay. So again we can combine all these 3 summing junctions into a single one, okay, if we intend to, right? So this is the way, okay. So you can see that one after another, right? The summing junction basically is equals to this, okay, one single summing junctions, okay, with multiple signal going in, right? So that is the case, okay. Same thing here, okay, basically they are branching off at the same particular point, right? So from this form we can transfer into this, okay. So next what we can see is that here is a series form, okay. We can cascade these 2 together into G3 G2, okay, G3 G2, okay, G2 G3, okay, combine them together, okay. Same thing here. Now because this is going through one point reaching out to the summing junctions, same thing branching out from this point going through H2 and to the same point again, okay, reaching out to the same summing junction. So you can see that they come from the same point reaching at the same point, okay. So this is the characteristic of a parallel block diagram. So here we can see that H1, H2, and H3 basically are parallel, okay, because they have a common input and common output. So since they are parallel, then we just group them together, okay, into a single transfer functions, okay, such that we have H1, H2, and H3, add them up together, right? Add them up together. But then what happens is that when we add them up together, what happens is that we can see this sign minus, plus, and minus, okay, minus, plus, and minus. Our intention here, okay, when we form this simplified so-called summing junctions later on, okay, we would want it to be minus, okay, so that it is the same like the feedback controls block diagram itself, okay. We want this to be minus. So what happens is this is minus, no problem, but this is plus, okay. This line with H is plus. So what we can do is that we change this to minus, okay, by adding a minus inside, okay. We transfer this minus sign into the transfer functions, okay. So plus, we change this to minus, alright, so that we can put a minus here. So that minus multiplied by minus, we get a plus later on, right? So after we can see that every single output going into the summing junction is minus, okay, by transferring the sign to the transfer functions, now we can do the actual additions, okay, inside the transfer function. So this is parallel, so we can have h1 minus h2 then plus h3, okay. So eventually they will branch out and give us a negative signal, okay, negative signal later on, right? So this is very close to our feedback control system now, right? The only thing left out is this, okay, there is G, okay, that we intend to move inside, okay, so that there is only one signal going in, feed forward block, feedback block, and output, okay. That is our familiar form of feedback control system, okay. So in order to move this block, okay, after the summing junctions, okay, as we have learned previously, once we move this in, okay, then we have to add another block over here, which is 1 over G1, okay, 1 over G1, right? So we move it in, then we will add another block here, 1 over G1. So once we add this into here, what we get here is now this is in series, right? Okay, so if this is in series, then it could become G1, G2, G3, right? Whereas on this feedback side, okay, we have this divide by 1 over G, right? So meaning to say this feedback side we will divide by G1, okay, for the whole terms, right? So that's all. Okay, so once we have that familiar form, okay, this block move in, right, it's familiar form now, okay, so immediately now we can form our transfer functions for this feedback form, okay, by having the upper one, okay, the whole block at the upper divide by 1 plus the whole thing at the bottom multiplied by the whole thing at the transfer functions, right? So we have G2, G3, G1, okay, multiplied by this whole thing over here, right? But since this side we have G1 also, so we can see that G1 cancel out with another G1 there. So eventually our equations would be G3, G2, G1 divided by 1 plus G3, G2 multiplied by H1 minus H2 plus H3. Okay, so this is our simplified form of this particular system, right? So this is how we can transform or simplify our block diagram, right? So that is the purpose of simplifications, right? Here is another examples, okay? Looks like more complicated, but again the idea is the same. Recognize the so-called familiar form, okay, before we move on, right? So the problem is that the familiar form may looks weird, okay. This is because when we draw, okay, sometimes even ourselves, especially when we draw it in a computer, right, then sometimes we just want to say this signal we tap it here, right, this signal we tap it here, okay, this signal we tap it here, and so on, okay. So in order to help us, okay, so again you can see that this signal directly tap going through without any block, okay. So when this happen, okay, like this kind of signal, this is a unity signal, meaning to say it actually have a transfer functions of 1, okay. We don't say they don't have transfer function, only the transfer function is equals to 1, okay, because whatever signal going in through these transfer functions we multiply by 1, okay, you get what is the output, okay, exactly the same, right? So to helps you, okay, you so that you don't miss it out later on, sometimes you just represent this with another block, 1, okay, so that you don't miss this out. Right, then okay, let's go through it easier. All right, so this become 1, right? But the problem is that this point and this point, here you have a branch and so on, so you may not see a parallel form. Okay, this point they do a summations, okay, but this point they don't go through the same point again, so it could be difficult. So in that sense, if we able to move this G transfer functions out of here, okay, just move it out. Okay, so if we able to move this out over here before this branch off, then it would be much easier. Okay, so what we can do is here, once we move this out, remember when we move into the parent or the main pipe, okay, then this one would have the effect of 1 over G, right? So this is G2, so this is 1 over G2, so we can rewrite this as 1 over G2, right? So this point now having moved here because this have moved into the parent, right? Now immediately you can see that this is a something very familiar, right? Okay, then also this side, okay, let's talk on this side. So this side there is multiple signal going in, okay, but all this signal is just once we combine them together at these summing junctions, basically it become an input. Okay, so once this become an input, this is again a familiar form of a feedback, a small feedback control block diagrams over here. So we can first simplify this, okay, into G3 divided by 1, since this is minus, then 1 plus G3 H3. Okay, so we can simplify this into this form, right? So remember, we recognize the familiar form, we form it. All right, so we successfully convert these two things now. Okay, slowly we will move on the others. All right, so the task could be difficult, okay, at the beginning, but slowly you just see which part you can move. All right, by doing this, as long as your equivalent block diagram is right, okay, you don't make any mistake over here, no matter how you move, okay, you will get the same answer later on. Right, so some people would like to move this side first, okay, some people would like to move the other side, so it depends on which familiar form that you have recognized previously first, okay, what is come into your eye first, okay, so you can do that. Okay, so once we have this familiar form, now again we just check this part. So what happened is that this signal going in, this signal going in, so this V4 is a kind of signal, right? This V4, okay, going through this branch and going through this, they are actually V4 and V4 multiplied by 1 over G, right? So when they add them up, what is the signal over here? So basically this whole part, okay, is the 1 over G2 plus 1, okay, because our signal is V4, right? So this, we have a block called 1, we have another block called 1 over G2, okay? So these two are parallel, this point and this point is the same point, okay, these 2 points is the same point, going out and then reaching the same summing junctions, okay, so they are parallel. This part have a transfer function of 1. So eventually you can add them up together, 1 over g2 plus 1. Okay, so this we further simplify, okay, removing this one into this form. Okay, so now it's become more clearer, right? So it's clearer now that this side, again, this is a feedback control system, okay, that we can group them together. Here is another one, right? But what happened is, if possible, we would want to move this in. Okay, we want to move it in so that these two summing junctions now can be merged together, right? So that at the end, after we move this in, these two summing junction can be merged together, right? So if we want to move this in, then we would have g1 multiplied by g2, and then there is an effect of dividing by g1. Okay, so we update our transfer functions here, then we have g1 g2 and then h2 over g1, right? So this after we move this over. Okay, so after we move, now again we can group these two together, okay, and since both are negative, then that would be great, right? So since they are both minus, then this is a parallel form, right? They are parallel, so parallel, we just have to add them up together. So have h2 divided by g1 plus h1, okay, add them up together. So this is a familiar form. Here is a series, okay, series, we just multiply them together, right? So this is a familiar form, okay, of feedback control system, right? Again, we can later on transform this into the simplified form of g1 g2 divide by 1, here is minus, so plus g1 g2 multiply by these transfer functions. Okay, so when you simplify them again, you will get this. Alright, so this continue in as a single block, okay, and series with the other block. So when it becomes series, then you will get this simplified, okay, very simplified blocks, okay, from the original form of multiple blocks, okay, multiple loops, okay, into purely one block, okay, with one single transfer functions. Okay, so this is how we can simplify our block diagram, okay, into one single transfer functions. Okay, so these transfer functions may look complicated, all right, but don't worry, this is the real operations, okay, of systems. Okay, they are interrelated. That's why the transfer function will be look complicated, right? But with the help of software nowadays, this can be solved, all right, easily. All right, so what we need to do is we know the idea behind it, how we can simplify it, right? So that we can, as an engineer, not only using the software, but we also able to validate the output of the software. because any software is made by human, okay, it's being programmed by human, okay, it can be programmed by yourself as well, okay, so you are the one who actually coding it, or someone will code it, right? So before you use it, okay, if you generate any result, okay, you can just put any input, you can generate the result. But how do you know whether this result is correct or not? Okay, this is how you can do your own validations. Okay, meaning to say you can put your knowledge into practice. Okay, you put random any blocks that you want. Okay, then you form into an equations. Okay, now you calculate, okay, what would be the output, and then you compare it with the simulation software. Okay, if this equations or these transfer functions, after you get it, is exactly the same with the simulation software, okay, that you will use later on, okay. It could be MATLAB or Scilab or whatever it is, okay. Then, meaning to say, it is right, okay. You put the right things, right? So here are some of the rules, okay, that you can see, okay. But basically this is exactly the same as what we have discussed previously. Moving in after the the summing junctions, okay, moving after the branch point, okay, moving before the branch point, okay, moving before the how should I say, the summing junctions, okay, and the familiar feedback control system. So you can recognize this, okay, then everything would be fine, okay, after that, okay. Then also you'll be able to do the series and parallel form of simplifications, then everything would be fine, okay. This is just like the algebra of it, okay, the plus, minus, multiply, divide, okay, operations, okay, but in the form of diagram and translate into a transfer functions, right? Okay, so next would be on a closed loop system. Remember, the closed loop system would looks like this, okay, closed loop system, okay. When it's being subjected to disturbance, okay. So if you have a disturbance now, okay, what is disturbance? It can be in any form of signal or input that disturb or change your parameters. Let's say you intend to hit, okay, you intend to hit this glass, okay. So you put a input of hit, okay, that would be your input, right? But what happened is that you have a disturbance, like suddenly there is a very strong wind blowing it, okay, or suddenly you are pumping out the water, okay, into my mouth, right? So that would be a kind of disturbance going through the signal, okay. So how the system will react, okay, that is our main intentions, okay. So the system or the disturbance can come into in a form of a direct parallel with the input, okay. So in that sense, we just plus and minus it in the summing junctions, okay. But sometimes it is passing through some controller block, okay. The signal may come in another form, like you may have let's say a disturbance of signal by electromagnetic wave or whatever it is, okay. So that kind of disturbance will be injected in the line of your block diagram, right, as shown here, right. So you may have a regular feedback system, okay, regular feedback system, when you don't have this disturbance, okay. But then this disturbance can come over here. If it is come over here, you just add them up, very fine, right? But when this disturbance come after a signal or a block, okay, then we have to do some kind of operations to actually take into the account of the effect, all right. Okay, so what happened is that in order to do that, okay, we will analyze such that this disturbance as also one of the input, this R as one of the input, okay. So after that we would combine the signal, the output signal, okay, due to the disturbance and the input itself, okay. So we try to isolate our problem, okay, by putting off this this input signal. Okay, so let's say now we put the system at rest, we call it as rest, then meaning to say this input is 0. Okay, then only disturbance is coming in. Okay, let's say we don't do anything, see what this disturbance will do, okay, on our system, right? So here we will put this RS as 0, then we calculate the signal as such. Okay, so when this is removed, what happens is that you can now reorder your view, okay, such that this is your input and this is your feed forward. Okay, then your feedback will now going through H and G1, right? Can you see that? It would become H and G1 as your feedback. Okay, input, okay, and this would be your feedback, right? So this is the considerations that once this coming back like this, okay, and then you will get this familiar form of feedback transfer functions. Okay, the G2 divided by 1 plus, okay, y plus, because here is minus. Okay, if we transfer this minus over here, then the minus will be here. Alright, so I hope you get this. Even though here this is plus, okay, we intend to get this as a minus. Okay, so how we get this minus? Since H is minus, we move it over here. When we move this over here, okay, this minus effect would be over here, right? So when we, let's say this is a series, this will be minus H multiplied by G1, okay, and this minus we can transfer it here, then it will be G1H, right? So eventually we have G2 divided by 1 plus G2 multiplied by H multiplied by G1, right? So this is our response, okay, due to the disturbance itself, okay, only the disturbance, right? So in this case, if now if the G1 and H, okay, since we have this H transfer functions, okay, because of this itself, we can have this H very high, so that these two conditions is correct. When this H is very high, then it will be much greater than 1, and because of that, when this H is very high, then this would become almost 0. Okay, so meaning to say the effect of the disturbance is now being suppressed. Okay, even though this signal coming in, because of this transfer functions of H, okay, it will now try to neglect, okay, too high, okay, such as it's neglect the disturbance itself. Okay, it suppress back the disturbance itself. Okay, so this is an advantage of a closed loop system. Okay, with this H, now we can control such that this disturbance become so-called negligible at some point. Okay, if you select a proper value of H over here, right? So this is how we can control it later on, right? So this is one of the advantages of a closed loop, that you can play around with this feedback, okay, so that you can remove or neglect certain disturbance, okay, if it's not too high. Okay, then another after that, we now want to see if without disturbance what actually happened. Okay, this is the original form. Okay, so respond respect to the input itself, the R input itself, what would be happen. So it would be very straightforward. These two cascade together in the series form, and then we can recognize feedback control loop, right? So we can have G1 G2 divided by 1 plus H G1 G2, right? So in this form, right? So this bottom denominator is exactly the same with this previous one, right? The only difference is the upper okay, upper is different, right? So eventually this output is basically the summations of these two, okay.
Kalau untuk zone ni, kalau Pak Iman,
Alright,
saya sudah
so now look back in this feedback control system due to the input of R only, right? So this input system inside, right? Again, if we can able to control this feedback transfer function, the H itself, okay, such as it's very high, then eventually these closed loop transfer functions would become independent of G1 and G2, okay, and is inversely proportional to the H, right? Just when this very high, these two become very small, right? Then it becomes like 1 over H sort of, okay, in that kind of a relationship, right? So again, because of that, okay, then the variations of G1 and G2, okay, would somehow not affect much on the transfer functions, okay. That's why this feedback transfer function would be critical when we select it properly, okay. When this H value we select it properly, it can actually remove the effect or buffer the effect of the disturbance, one thing, okay, and at the same time it helps to mitigate the variance of this G1 and G2, okay. When a signal coming through G1 and G2 which change very much, okay, it will still not responding suddenly to a certain response. So that if G1 let's say we plot into a graph, then if move, then suddenly go very high, then go to another very high, okay. We don't want this kind of signal which would be very hard to control at the end, okay. So by having this feedback, okay, we can actually lower down this disturbance as well as the effect of this G, okay, along the feed forward directions, okay. That is the advantages of having a feedback control loop, alright. So whatever output, we bring it back and compare, so that it actually helps to lower down of all this sudden change, okay, throughout the system, okay. We don't want this kind of sudden change that create a very large error at the end that we not able to control, right? That is the main advantages of closed loop, okay, as compared to open loop, right? So now, as we have seen, okay, so if we can investigate the disturbance and the input signal, okay, their response to the output, okay, we just combine them together, then we combine them together to form this form, right? So which would be in this, okay. So this is the equations that you may get, okay, once we have this, okay. So again, if you can recognize this familiar form, okay, which may not be quite often in this course, okay, means throughout this whole semester, but it would be very useful, okay, when you deal with system design later on, right? Any questions before we move to the last sections of signal flow? Guess maybe still processing, all right. So we move on to the signal flow graph, all right. So signal flow graph is another form or alternative to the block diagram, right? And basically the signal flow graph consists of branch and node, okay, only branch and node. So now we don't have block, that's why we don't call it as block diagram, but only a branch, and not that represent the branch will represent a system. Okay, previously remember we used block to represent the system, but now we use branch, okay, which is the arrow, okay, to represent a system. Okay, whereas previously we used arrow to represent the signal, but here we use not to represent the signal. Okay, so how it will looks like, it will looks like this. Okay, every single node is the signal itself. Okay, signal itself. Okay, whereas this line, okay, we call this as branch, the line itself is the transfer functions or the system. Okay, sort of like reverse of the previous block diagram, right? We call it as a signal flow, right? Our main intention is to see how this signal flow from one node to another node. Okay, so signal at one node transfer to another node, right? So we call this as signal flow diagram, right? So again, very similar. Okay, signal flow from point, this signal R2 will flow through this system, okay, into another node or another signal, right? That's it. Okay, so how we can do this is that we can again do similar operations. Okay, the operations very similar to the summing junctions, okay? Very similar to the summing junctions, such that if you know, let's say we take this point V, okay, as our final signal here, right? Our intention is to see how many signal actually going in, right? So this signal will now equals to R1 multiplied by G1 plus minus G2 multiplied by R2 plus G3 multiplied by R3, right? So this is how we sum them into one node. Okay, and then now we also branch it out. Okay, so when we branch out, then we have different node, right? So every single node of this we can later on investigate. Okay, so now let's say we want to see C2. Okay, we want to see C2. Okay, so what is C2 is that this signal V multiplied by G5, we get C2, right? So this is the form. Okay, so how we can do it? Okay, so since we have V, this whole thing we put it in, so this is our form, okay, which is longer. So this is the way of doing the operations to investigate what would be the signal at every single node. Okay, that's it. Okay, how we can actually transform or to draw this signal flow diagram? First, we just draw node, okay, to represent the signal. Okay, then we connect them with line, right, to represent the transfer functions. Okay, we would want to write the transfer functions next to the line. Okay, and finally same thing, we can simplify them, okay, if we want, right? So this is how we can convert a block diagram into a signal flow, right? So we have a general block diagram, and this block diagram what we do is that we identify the signal, right? So this signal would be here, the R would be one signal, here x2 would be one signal, x1 will be one signal, and C would be another signal. Okay, so we represent all this into node, right? Then since this signal will go through one block, so go through, so just draw one arrow, okay, to connect them from R into V, okay, going through this, okay, and we put this G over here, okay, G1 over here. Then here from x2 into x1, okay, another going through, so going through G2, so we will write in this form. Okay, so eventually we form this so-called signal flow diagram, converting it from a block diagram. Okay, so same thing for parallel form. Okay, so parallel form, now it branch off, right? So even though it's branch off, doesn't matter, right? So again, this is the input R. Then after, so you just recognize after the block diagram there is one signal. So we have this x1, this should be x1. Okay, so this should be x1, this should be x2, and this should be x3, right? And then here would be our CS, right? After the summation, so we just going through this G1, okay, going through this G2, going through this G3, right? Then after that we sum them up together. So all these three signal going into one signal, so going into one signal. But how we going to connect them together? There is no block diagram, right? There's only one summing junction. So what we do is we put 1 1 1, okay, to represent the transfer functions. Over here is actually 1, okay, 1 1 1. Okay, you may want to put -1 or 1, okay, to represent plus minus, okay, up to you. Okay, but going through the summing junctions, we will put 1 1 1, okay, so that after that which we sum at this C, okay, as our output, right? So this is how we would form from a block diagram into a signal flow diagram. Okay, same thing with a feedback control system. Input, output, okay, input, output, error, right? And since this is going back to the error, though, so we don't draw any additional signals. This is the same going through from this point to this point, right? So we would write R going to E through these summing junctions, and that would be equals to 1 because it's plus. Okay, then going from E going through C, going through transfer function of G, so we just draw an error with a function of G. Then at this point it flows back, okay, it flows back from signal C to the signal E, okay, signal C flow to the signal E. Since this is negative, then we have to combine it into our transfer functions, okay, negative, because we cannot see the -1 there, okay, unless you can also draw another knot here to connect it, okay, up to you, right? So this is how you can form the signal flow itself, right? So that's all for this sessions, okay, so you can try this block diagram, and also this one, okay, so this one is the block diagram, you try to simplify it, okay, and this one is the signal flow, okay, you just try to convert from this block diagram into a signal flow, right? So that is your exercise, right?